This example is somewhat different from the last ones, simply because of the directions involved. So watercraft has an initial velocity of 6.4 meters per second east. We can define that, VI. Undergoes an average acceleration, keyword here average, of 2.0 meters per second squared south. For 2.5 seconds. That would be delta t. What is the final velocity of the watercraft? So what is VF? What makes this different is that we cannot just flip the sign of one of the directions to make them match up. If we flip VI to negative, we would get west. If we flipped average acceleration, we would get north, and we get nothing matching. So we need to deal with this in terms of a triangle. What we know is that the watercraft, its VI is to the east, which would mean it is going this way, 6.4 meters per second. We know it accelerates to the south, so it is accelerating this way. That would not be 2.0 meters per second squared because that's the acceleration. We don't know the velocity towards the south that it has. But in the end, after the engine fires on this watercraft, the watercraft is actually now moving in this direction. And this is the final velocity that we need to find. So we need to know after the watercraft accelerates, how fast is it moving to the south? Well, we know average acceleration. We know the time. We want to know the velocity to the south. And because we have average acceleration, we can use one of those simple formulas. Average acceleration equals delta V over delta T. Average acceleration 2.0 meters per second squared. Change in velocity to the south, we don't know. Time was 2.5 seconds. Cross multiplying, we get that delta V would be 5.0 meters per second, and this is to the south. So we haven't even dealt with the piece that's moving to the east. We've just been dealing with the piece that's moving this to the south. So we have 5.0 meters per second to the south. And now we have enough information here to determine the overall final velocity. This is just a right triangle. We can go to Pythagorean theorem. Substituting in, I'm going to call 6.4a and 5.0b. C is what we're trying to find. Working that out, 6.4 squared is 40.96. 5.0 squared is 25. We get 65.96 equals c squared. Taking the square root, going to 2 sig figs, we get 8.1 meters per second. Now that's not quite enough because this gives us the speed of the watercraft but not the velocity. The velocity also has the direction with it, and we can't not just say that this watercraft is going southeast. We need a specific angle. So I'm just going to clear off the page, sketch this all out again. We need the specific angle here that this watercraft is now traveling at. For this, we go back to SOHCAHTOA since it is a right triangle. If we deal with the sides of 6.4 and 5.0, Again, that's first-hand information, always best to go with that. We can use tangent, which is opposite over adjacent. Five being the opposite side, 6.4 being the adjacent side. Calculating that out, making sure you're in degree mode when you do it, we would get 38 degrees. So now we can put this all together and say that our final velocity is 8.1 meters per second, and we are 38 degrees south of east. And as we've dealt with before, we have two ways that we could possibly show this direction. This way, or we could say 8.1 meters per second starting east and moving 38 degrees to the south.